Now for an example. In our examples, we're going to get a chance to rummage through one of the most important tools for Sam and Dean, and where they store their weapons to fight, and that is Dad's car. We'll use the weapons we have gathered so far to predict the entropy values based on comparison of groups given. Remember, this is the time to build a strategy to approach problems. You want to complete the problem with me and then think of a way to approach the problem that will make it easier for you. Let's gather all the expressions, relationships, understandings, assumptions, etc. to the table, and then go ahead and figure out a plan to answer this question. This question says, predict the relative entropy values. Choose a member with a higher entropy in each of the following pairs, and justify your choice. Assume constant temperature except in part E. So this is going to be the only part where we don't assume constant temperature. Everywhere else, we can assume constant temperature. So my plan for this example is to write down what I know. Particles with more freedom of motion are going to have more microstates. When you increase your microstates, you're going to increase entropy. And also, in order to increase the standard entropy, you can increase temperature, you can have a dissolution or create a solution, for example, and of course that's going to depend on the solvent itself. And also, you can increase molar mass or complexity. But of course, when you're talking about molar mass and complexity of substances, you need to make sure they're all in the same phase. Since they're asking me to choose the member with the higher entropy in all of these pairs from A through F, the first thing I'm going to do is check the phase. If they're in the same phase, I'm going to compare them based on molar mass and complexity. If they're in different phases, I'm going to compare them based on whether or not they're a solid, liquid, and gas, with the gas phase being the higher entropy. If they're going to be based on temperature, I'm going to be going off of an increase in temperature is going to mean an increase in standard entropy, for example. So let's go ahead and start with letter A. We have 1 mole of SO2 gas or 1 mole of SO3 gas. Which one is going to be the higher entropy? Now, of course, since we're talking about things that are in the same phase, we're going to be dealing with molar mass or complexity to help us make this choice. Okay, so between 1 mole of SO2 or 1 mole of SO3, I'm going to choose 1 mole of SO3 because we have more atoms here and a higher molar mass. And anytime you have equal number of moles of substances with the same type of atoms, meaning sulfur and oxygen, in the same physical state, which is gaseous here, the more atoms in the molecule, the higher the entropy, or again, just straight up going off of complexity. Now let's go to letter B. We have 1 mole of CO2 versus 1 mole of CO2. But this first mole of CO2 is in the solid phase versus this mole of CO2, which is in the gaseous phase. So when we have different phases, we go off of solid, gases, and liquids. Therefore, I'm going to choose 1 mole of CO2. Again, for a given substance, entropy is going to increase as the phase changes from solid to liquid to gas. Let's go ahead and go on to letter C. Here we have 3 moles of O2 versus 2 moles of O3. They're both in the gaseous phase. So if they're in the gaseous phase, we're going to verify them based on molar mass or complexity. But guess what? We actually have to have a little bit of a nuance added in here, because if you go off of complexity, you're automatically going to go to O3. But guess what? There's only 2 moles of O3 molecules floating around versus 3 moles of O2 molecules floating around. So even though we're in the same gaseous phase and we tend to go with molar mass or complexity, what's going to supersede both of those things is the number of microstates is going to increase the number of entropy. And how do we know that we're increasing the number of microstates? Based on the number of particles. Since we have way more moles of the O2 gaseous molecule, that's going to supersede having 2 moles of a more complex molecule. So the higher entropy is going to be 3 moles of O2 gas. When we look at both of these amounts, we see that the 2 samples contain the same number of oxygen atoms. If I do 3 times 2, that's going to be 6. If I do 2 times 3, that's going to be 6 as well. And although the O3 molecule is more complex than the O2 molecule, the greater number of molecules are going to dominate because they're going to have a higher amount of microstates. And so the higher amount of microstates is going to give the higher entropy, which is what the question wants. For letter D, we have 1 mole of KBr solid or 1 mole of KBr aqueous. So we have a solid version of KBr here versus an aqueous solution version of KBr here. Even though they have the same number of ions, because they are in different phases, we go off of whether or not they're solid, liquid, or gas. And since this is going to be aqueous, it's going to supersede the solid. Why? Because, again, the motion is going to be increased when you have an aqueous version of these ions versus if you have a solid sample. In the solid sample, we know the motion is going to be limited, the energy is less dispersed, and of course that means you have a decrease in entropy. Now for letter E, we simply have seawater at 2 degrees Celsius or at 23 degrees Celsius. Since seawater is the same, it's going to be liquid seawater at that point. All we see here, all the information they give us, is an increase in temperature from 2 degrees Celsius to 23 degrees Celsius. So the one I'm going to choose is obviously going to be seawater at 23 degrees Celsius. Why? Because you're going to increase the state of standard entropy, of course, or have a higher entropy when you have a higher temperature. A simple way of saying that is entropy increases with rising temperature, folks. Now for letter F, we have 1 mole of CF4 gas or 1 mole of CCl4 gas. Now again, we have two substances in the same phase. Now, complexity won't help us here because we have 5 atoms here and 5 atoms here. So we have to go off of molar mass. Now, one of the trends we saw before is that if we increase atomic size as we go down a group on the periodic table, that is going to therefore increase the standard entropy. So when we have fluorine here and chlorine, since they're both attached to a carbon, I can go off of the fact that fluorine is smaller than chlorine and automatically choose 1 mole of CCl4 gas as the one with the higher entropy. Now, of course, instead of doing that, you could go and calculate the molar masses for yourself, but just by using that trend that we saw before, since I know that chlorine is larger than fluorine, if I have 4 chlorines versus 4 fluorines, then this is going to give me a higher molar mass. Again, which is why I choose it as my answer. You can also simply say, for similar compounds, entropy increases with molar mass.